So yeah, how natural are artificial neural networks? Like, neural networks were uh, came up to sort of study, as OP said in the morning. There were two groups of people, one thinking about neural networks, the other about artificial intelligence, and they were pretty separate. So the people, they tried to actually model how brains work using neural networks, right? Composed of neurons. So today we'll try to see one segment of the approach to understand brain using neural networks, where it works, where it doesn't work. So we'll go through these couple of um, topics. One is I'll try to motivate how in the brain you have neurons, and from the morning you have heard of FHN, Fujinagumo, Hodgkin Huxley, and all these complicated models, but I'll just cut everything and say it's a switch, right? Then we'll go to linear perceptrons, which OP talked about. Like Rosenblatt came up with this particular first neural network, which was called the perceptron. And yeah, little louder. Okay. Or if they can increase the volume of the mic. Okay. Um, Better? I can hear myself uh, from the feedback. Okay. So linear perceptrons, and where Papert and Minsky came and like said that this is not really good and this is where it fails. We'll actually look why it fails and how we can make it work again. Then we'll go to multilayer perceptrons. You guys will have probably heard of feed-forward neural networks, like in layers, and you train it using backpropagation. Then we'll look at convolution neural networks and see where it fails. Right. So the complexity of the brain is a lot, right? So this picture essentially tells you all the regions associated with visual information. Like you receive an input through your eyes, and then it goes through different it excites different parts of your brain, and you change the direction in which you're seeing, you walk, or different things like that. And it also has memory involved, like you remember the things that you see. So the unit is a neuron, which is like this is I think it's stained, and you can see the neuron, and this is sort of a picture of that, where you can see the three main regions of the neuron. One is the dendrite, which is on the top over here, which receives the information. Then you have the soma, or the cell body, which does some sort of processing, and then the axon sends the information down after the processing, sends the information down to the downstream neurons, right? Now this has the brain has a lot of complicated, complex structures, like so many kinds of neurons. Actually, the OP had a better visualization, like a better picture of that. This is just a cartoon drawing, but you saw the different kinds of neurons that he showed in the morning, and so I mean a switch compared to this, right? And then it also has different kinds of neurotransmitters, right? So synapses, where the connections are made. Oh, I actually have a pointer, right? So the synapses, where the connections are made from the neurons which are coming from above, they can also be of very different types. There are also these neuromodulators which sort of are not exactly come into play in the synapses, but they sort of overall modulate how the neuron is behaving. So there are a lot of complexity, but what we'll do is we'll think of it as a switch. How does the switch work? We're focusing on this particular neuron, so it gets its input from the other neurons which are connected to it, and with different weights, right? So the synaptic strength sort of the W's, the weights, sort of embody the synaptic strength of the neurons connected to the central neuron. Now the processing that the central neuron does is it takes a summation, weighted summation of the inputs received, that is W, Yj, Vj. So this neuron I am calling it as Y, and this is 1, 2, 3 up to n, right? So the input of the yth neuron is weighted sum, right? Everyone's comfortable with the summation symbol, right? Okay, so j not equal to y was not necessary, but anyway, wij vj, and then it sees if the total input that is being received by this neuron crosses a particular threshold. If it does, it switches on. If it doesn't, it stays off. So here this step function like thingy is essentially, if it's less, the input received is less, it's 0. If it's more, it's 1. So it stays off or it stays on based on the amount of input received, right? Okay. So this particular type of switch like behavior was first sort of said by these two people, McCulloch and Pitts, in 1943, where they thought of neurons doing binary operations. So if they're doing binary operations, you can think of now what kind of neuronal structures you can make so that any truth table can be made. So they boiled down the computation problem to finding a set of connections, set of neurons, so that a Boolean operation or a Boolean truth table can be made. So this is some of the examples that are there in their paper, like this is the OR, this is the AND, this is and a NOT. So we'll actually try to see how we can make these gates. So we'll do two very simple gates and an OR using these perceptrons, these switches, neurons, right? So in essence, what Rosenblatt was doing. So this we over here. Oh, yeah. So I had the slide in Google Slides. After taking it to PPTX, things have sort of gotten a bit funky. But this is X and Y. Wait, have I? It's ulta, no? Sorry, I think. Yeah, I think. Actually, this is OR. I have put AND over here. This should be OR. Please gloss over that. But yeah, so let's try to make a OR gate out of this. So the thing that we have are these input neurons, right? So we have these input neurons which can take these values, this X and Y. So this are X and Y, and we have this output neuron, right, which we want it to calculate X or Y, right? What we have to figure out is what weights do we give it to them. So remember, the way these neurons do computation is using this. So in this case, it will just be Wx into X plus Wx into Y and then a threshold, right? This will tell you if it's if it's positive, then this will turn on. If it's negative, it will turn off, right? So if you look at this problem in the input space, right? Yeah. Sorry, what are you saying?
The equation that you y, like this y actually is like X equal y. Is that no, not this one. That W of X, yeah.
Sorry.
That is supposed to be y.
This is supposed to be Wy, yeah.
Yeah.
Nice, you guys are following. Okay, so if you look at the input space, what I mean by the input space is we put this X and Y in 2D, right? X, okay, let's put this as Y and this as X, right? So if we look at that, then it's sort of like this. When they are like either one of them are on, this final neuron should fire. If they're not on, then it should not fire, right? Now, so the way we need to decide the, so here the W's are, so let me just show you the answer, sort of like this, right? So these weights are of unity 1, right? and this is a threshold of 0.5, right? So if I put it over there, what I get is x plus y minus 0.5, right? And it should now be obvious that if x is 1 or if y is 1, it's going to push it above 0.5, and so this neuron will turn on, and you have gotten a AND gate using 3 neurons, right? 2 input neuron, 1 output neuron. Let's look at a OR. Sorry, and sorry, an AND. So this is what the input space should look like, and okay, by the way, this thing is called a decision boundary. So on the one side of decision boundary, it's turning on the other side it's off. Yeah.
Space in between 0 and 1 are not really meaningful, right?
In this case, yeah, it's not really meaningful.
Okay.
Now you can generalize the problem to have way more input.
Continuous.
No, not continuous. You can have way more input neurons. I mean, you can also have continuous.
X and Y can be continuous as well.
In some cases they do use it, but usually they use binary. Okay, so and it should be clear that the answer to this, like, you again have 1 for the weights and 1.5 as the threshold. So only if both have turned on, the decision boundary will be this, and if both have turned on, only then it will fire, right? Okay. So now what was the problem of this that Paperton-Minsky showed? So if you look at the XOR gate, it looks something like this, right? And how will you do something like this? So you will essentially need 2 decision boundaries, right? Because these 2 are on, but these 2 should be off. So you need 2 decision boundaries to do it. But over here, you can actually make 1 decision boundary. So anyone wants to guess what? Yeah. Yeah, XOR gate is essentially this truth table, where
in terms of the logic.
In terms of the logic, it's on XOR. So it's on only if one of them is on. If both are off, it's false. If both are true, it's false. Okay, on, true, I'm using it interchangeably. Off, false, I'm using it interchangeably. Yeah. So that's what a XOR gate is. Like, you have only these 2 as your true state and these 2 as the false state. Yeah. So any ideas what we can do? What they realized was that you can actually have hidden layer, right? And so each hidden layer contributes a decision boundary on the input plane. So you have this OR. The OR decision boundary is this one, and it says everything on this side. It will turn on for every point on this side. This one and will turn on for everything over here, right? And if you take a combination of this with this turned as negative, right, then this decision boundary where this one was on will essentially flip, and it will say this, it won't turn on with this, it will turn on with these 3. Am I making sense? Not following? Or okay, yeah, so you guys are comfortable with what happened over here? Now that is exactly what I'm doing over here, an OR gate and an AND gate. Okay, yeah, OR gate and an AND gate. Now imagine the OR gate is exactly the same. It's like an OR. It takes input with the threshold of 0.5 and sends over if it's on or not to the final neuron, right? So the decision boundary corresponding to OR is this big green area. Now the decision boundary corresponding to AND, right, is over here. But if I take minus AND or not AND, then it will flip to this, right? So it will be on only if all of them are not on, right? So the decision boundary essentially stays the same, but it flips, right? So that's what we are doing here. That's what's happening over here. We have an OR which sends over the same input to the final neuron, and we have an AND which sends over the flip flipped input to the final neuron, and that's why you have a decision boundary facing this way and another decision boundary facing this way, and that's how you get this particular area which is on, right? So what do we get to, why does it, why is a single, so two of the hidden nodes actually contribute two decision boundaries. So any non-monotonic function or non-monotonic truth table can be approximated if you have a hidden layer, but in case of single layer, like if you don't have any hidden layer, there can be only one decision boundary, and so you cannot make a non-monotonic truth table, right?
Can you explain a bit the concept of hidden layer? Why you call it hidden?
It's hidden. Okay, so since we know what that this has to be and this has to be or, and the and has to be flipped, since we know this, that's why it's not really hidden to us. But consider a very complicated problem of, let's say you have to find this decision boundary, right? Then we actually don't know what these hidden layer will actually capture, right? So the units in the middle layer, we don't know what they're capturing, that's why we are calling it hidden, right? In this particular specific case, we actually constructed it like that, and we know what the hidden units are supposed to be, that's why we could just say, right? Yeah. Yeah, so here if you observe the input space, once it's on, it never turns off, right? So you increase x or y or xy together, once it's on, it crosses this boundary, it never turns off, right? But here, once it's on, it crosses a boundary, once it's off at the starting, crosses a boundary, turns on, then crosses another boundary, turns off. So you have a non-monotonicity, right? That's what I'm talking.
And then the 4 arrows coming out of the first input layer.
Yeah.
But this is the same as on the first layer of that.
Yeah.
X and Y are the two nodes.
Yeah, x and y.
And what are coming out of those? The exact same input went in.
Yes, the AND gate, the network for the AND gate and the network for the OR gate. I mean these two, essentially this over here and this over here. Thanks for the questions.
What is the difference between red arrows and these?
Yeah, so the red arrows over indicate +1 weight, and the blue arrow over here indicates -1 weight. Maybe I should have written it down, but that's this -1 from this AND gate is actually what's making this flip, right? Yeah, yeah. It's
What's the nature of that?
It's the same as the other nodes. It also has a threshold. I didn't put in the threshold because that's an exercise. But it also has a threshold. It will receive all the input from these guys, and then so what will be the input at the final node? It will be, so if this is your x and y, these at the top ones are your x and y, and that's what these are, right? So at the final node, it will have x plus y coming from the OR, right? And then it will have sorry, x plus y minus 0.5. Okay, now here I'll fall into a trouble because I cannot just compose them. There is a it's because I cannot compose them, right? There is a nonlinearity over here, which is, even if it's 0.1 above the threshold, it will be 1. If it's 0.5 above the threshold, it will be 1. What I mean is the input that's coming over here, right? This particular output of a neuron and input that the neuron receives, right? So at the threshold value, what happens is it goes like this. So even if it's over here, very close to the theta but negative, it's still 0. And if it's here, just above the theta, it's 1. So there is this nonlinearity. So I cannot just compose them. Sorry, your face doesn't look nice. Tell me what's the problem. Sorry. This part? Last part? Yeah. While I was writing it, I realized that it won't work over here because I have to put this non-linearity in it, right? So I was just thinking of writing x plus y minus 0.5 coming from the OR, right? So I want to write what the state of this is as a function of these two, right? So that's what I was trying to do, but then I realized that it won't work out because so x plus y minus 0.5, this is the state of my OR gate. Then I have x plus y minus 1.5, this is the state of my AND gate, right? So this is the state of OR and AND, which are these two, right? Now I want to add them up to compute the final node's value. Then it will be OR gate, so this value minus AND gate, right? This OR gate, so the final whatever input this is getting is OR into 1 because of this weight minus AND, right, because the minus comes from this minus, right? So that's what I was trying to say, and there will be a theta to this final neuron. So if it goes above a threshold, only then it fires, right? So the question, the sort of homework or assignment was, what will this theta be? And it's very simple. You guys will definitely be able to figure it out. Are things clear? Yeah.
In the XOR gate, you said that the hidden layer is, so we don't know the thresholds of the hidden layer.
Yeah, we don't know what the hidden layers are actually doing. In this particular example, we know because it's very simple looking at the decision boundaries.
So in that case, how do we compute the neuronal
Activity?
for the XOR gate?
Uh,
When the hidden layers are not.
in this case, we know, that's why we have, but in case of more complicated truth tables, we won't know. That's where the next slide is going to come. Like we use something called backpropagation. Yeah.
So if I assume that the hidden layers are not known and xy to the final neuron output I have to calculate, then it will be just a simple calculation, right? Which will be an OR gate. If I am correct.
No, say that again.
So in the XOR model, because I don't know my hidden layers, so all I can see is xy, and which is finally computed to b. So because I don't know the hidden layer, I will consider it as either an OR and an OR gate or an AND gate, right? And it will be an OR gate.
Yes, in this case we can do it because we know what the answer is going to be. But in case of complicated functions, if you have this particular mapping that you have to do, you have this x vector, I am saying vector, in this case the vector has two elements. If you have a x vector which has x1, x2 up to xn, like multiple input neurons, and that has to say that the final y or the final neuron will say it's a cat, right? So how do I take the x vector and say that that's a cat? So we don't know what these middle layers are actually doing. We just know that it has to learn this correlation between x vector and cat or y, right? So we'll in machine learning or in AI or in these cases, what we have is we have this mapping that we want the network to learn, which is you have x vector, multiple x vectors, and which corresponds to a particular y. Y can be y or a y vector. So there are multiple examples like this. X1 vector should map to y1, x2 vector should map to y2, and so on. We want the network to learn these mappings so that when we get a new information, like new input, let's say x k vector, it will be correctly able to predict yk, right? Number of
Gates that we use, can you put a lower number?
Okay, that takes me to the second point, which is in 1989, this guy called Kurt Hornig, he showed using mathematics, I couldn't understand the paper, that this sort of a architecture where you have one input layer, one hidden layer, and one output can do arbitrarily complex decision making. So, a lower bound on the number of gates used. So, you can probably say that there will be a lower bound, but I don't think that's very, I don't know how to calculate that. I'm not sure if people have, I mean they have done it, I haven't encountered it. But in these ages you have heard of people doing neural networks with billions of parameters, thousands of layers, but in theory you can actually make do with only a single hidden layer. The only crux is you need to have that single hidden layer to be very large, exponentially large compared to the other networks. So essentially having a single hidden layer which is extremely large, what they're doing is they're having multiple hidden layers which are of intermediate sizes. Shall I proceed? All right. So this is linear perceptrons, and we saw a simple example of a XOR gate with a single hidden layer. Yeah. Thanks, Adrian.
Sorry, so you said that you have one single
Yeah.
that's exponentially large.
Yeah.
And that can essentially succeed in like what you said.
Yes. Yeah.
The outputs go as inputs into the other, and that is kind of essentially how that happens.
Yeah,
By
you-
neural waves, and then that's how the learning happens. So if you have one, so is there
I'm not sure how to answer this question. Wait, so this what is the neural network actually doing? It's taking in inputs, putting it through a nonlinearity, and then giving you the result, right? That nonlinearity is this, like in this case, it's step function or sigmoid, whatever it is, right? So in case of multiple layers, you have the input coming in, going through multiple nonlinearities, and then giving you the result. In this case, there is the nonlinearity is present over here, so it can still capture it. But it will take a large set for, okay. So let's consider a particular neuron which is in one of the pretty deep layers, like in hidden layer, but let's say in hidden layer 3 or 4, right? It is capturing some particular essence of in the input space, but that can also be captured with some hidden node in the first hidden layer by chance. But to have that chance occur, you have to take a very large network, very large hidden layer. Maybe it will become more clear in my next talk. Yeah.
The hidden layer is large. We need large number of outputs also. Large number of inputs also. It's not necessary.
No. I mean, what it will do is essentially it will have multiple. So in that example, what it will end up having is probably multiple or hidden. Like this hidden node is OR, so you might end up having another hidden node which is also OR, then another hidden node which is and so on, right? That will act. Sorry. Yeah. Yeah. So a single hidden node can represent the same thing as some other hidden node. This one doesn't really make sense. Let me get back to you later. Even I am not very, I don't really get this paper, but I know, okay, fine, mathematicians have done it. But we can talk about it later. All right, so yeah, so we'll go to larger networks, multi-layer perceptrons, and who have seen these before, like feed-forward neural networks, multi-layer perceptrons? Only a few. Okay. Oh wow! Slowly hands are raising. Okay, great. So the essence is it's supervised, which is you have certain input. It's doing the same thing, right? It's doing this. Whoever asked this question, thank you for asking it. It's doing this thing, right? you have this tuple of um, input value and the mapping to its output value, right? So, we want the network to learn that. So, how do we figure out what the weights are, and so how does it work actually? Let me just say, and this is what the forward propagation of information is, that you put certain weights, or you put an image, which we will see in the next example. You put an image in this, and that goes in the next layers, in the hidden layers, and then finally comes at the output where it predicts that it's something, right? And how does it go forward? It's a very simple rule, which is, you have this, which we saw, right, which is weighted sum of the previous layer plus a bias. A bias is essentially a negative threshold, same thing, right? So, weighted sum of the previous layer activity plus the bias, and then this input is passed through a nonlinearity, right, a nonlinearity like this, or something else, right. So, that is what happening in every layer. So, you have this input, it goes to the first hidden layer, sums it up, sends it to the sums it up, and then passes a function through it, function to it, and then it goes on to the next layer, and so on, right? Yeah.
I might have missed this, but previously my question was that the sum of weights of the inputs minus the threshold.
Yes.
Here it is
Plus bias.
is- So is it?
So you can, it's this, you can consider it to be the same, like, you know, theta is minus bias. Yeah. All right. So how do we learn this network? Oh, see, it said gradient descent. Only gradient is left now. The descent, I think, is behind that formula. Yeah. So this is around 1960s, early 1960s, when people were, I mean, when this was just starting, they were thinking how to make these networks learn. What is learning? Essentially the weights, right? Weights and the biases. How do we learn? How do they learn the weights and the biases? And the first example was probably Widrow and Hoff, who did this sort of a gradient descent. I'll come to that, on a single layered neural network, and they were able to train it. The idea is essentially, you have this cost, right? This cost is some function, is some function of the predicted output and the required output, right? So, this is y cap, that is okay, I tend to confuse y and y cap, but the idea is, you are comparing the output that you get from the network, right? So, you pass this x vector through the network, you pass the x vector through the network, and over here you have some y. Now, you compare this y to the actual y that is there, right, and that is your cost function. People use different kinds of cost function, but the idea is just that the cost has to be minimized, right. So, the gradient descent, what it does is, it does this iterative approach of changing the parameters that I've denoted by theta t plus 1. Theta can be either w or bias, like weights or bias, and essentially each iteration is going towards a minima of the cost function. All right. So, so people, gradient descent became a thing that time, and a lot of people around 1980s, I think starting from 69, Paul Verbos and then Amari and a lot of other people had some version of it, but the actual version that we are going to see now was done by Rumelhart, Hinton, and also a couple of other groups. It was very straightforward, because it was actually just chain rule that Leibniz did centuries ago, right. So, chain rule is very easy to apply in this, right, because you see this cost function is a function of y and y cap. Y is a constant, right, I mean, constant as in, you know, what is the empirical output, and y cap is your network output. the network output has these as has these inside, right? So it's very easy to see that since these are like normal functions, this is a linear function and this is some nonlinear function, you can actually see that the y cap can be differentiated, and that's what backpropagation actually is. So you have dou c, dou w I j l, which is this term, right? We're just calculating this term now, and then we'll just backpropagate w I j. So I'm calculating the weights, these weights, right? So dou c dou w I j at the layer L is dou c dou a I L. A I is the activity, and then A I depends on, so A I L is actually y cap fx, like y cap, the predicted output, right? So dou c dou the output A I L depends on z, so dou A I L dou z I L. Z I L now depends on w I j, w's, so dou z I L dou w I j l, and normal chain rule gives you the learning rule for the first weights. Second weights, same thing, you have dou c dou w I j l minus 1. So you want to calculate, okay, I haven't shown in the picture, but just the previous weights, right? So you want to calculate that, so you take the same route, dou c dou APL, that is the activity of the final layer. APL depends on ZP, so AL depends on ZL. The bracket ones are the layers, like these layers, everyone can see it, right? Is it okay? So dou c dou APL, APL depends on ZP, ZPL depends on AL minus 1, AL minus 1 depends on ZL minus 1, and so you get the learning rule for the previous weights, and so you can just back propagate this, right? Just chain rule, plain and simple, and that was successful up to some point. Yeah.
N minus 1 layer, you have some del c by del w. You have some expressions. Yeah, that expression. It doesn't depend on del c by del w.
Doesn't depend on del c del w. So very good point. That's actually a limitation. So you see, it depends on WPIL, WL. It depends on the weight. It depends on these weights. You see this WL, right? Yes. So what it actually means in biological sense, you are okay. That we'll come to that. But yeah. So the further away you are from the output, the further away you are from the output, you will require all the weights which are downstream of it, right? And that is very weird if you think about how brains work. But turns out that actually happens in our cerebellum. Yeah. But if you now let me just tell you a concept of a receptive field. So this is a video from a snapshot of 3 blue 1 browns supervised backpropagation. What are these pictures essentially? So in the first layer, so after the network is fully trained, all the weights and biases are trained, you can take these weights, right? So you take one of the neurons, you take one of the neurons out, and this neuron is connected to all the input, all the units in the input layer, right? This is essentially the weights, those weights. So you take one neuron, right, and show all the weights. So this is the weight. So this is a single neuron and the weight to the input. So you see how it's kind of noisy, and you can see certain patterns coming out. Like this might capture a 8, this might capture a 3, stuff like that. But you see on the edges, it's actually very noisy.
This is the handwriting recognition data set.
Yeah, it's done from that handwriting MNIST. Yeah. Did anyone get the idea of this? Is called a receptive field. So you take this. So this is your first hidden layer. I think, yeah, this is your first hidden layer, and you take one of the first hidden nodes and then look at the weights. So, this weight is what is there, right. So, if you get a 3, so if there is a figure which traces out this blue region like this, a 3 like this, then this node, the weights corresponding to which are shown here, the weights corresponding to which are shown here, this node will turn on, right. So, that is what the receptive field idea is. You look at in what field of view is the node actually sensing, and yeah, this gives a clear picture. Now, to your question, I mean your point. So, backpropagation requires upstream flow of downstream connection information, right. So, these WL is actually required for L minus 1 and so on. All right. Now, let us look at CNN, which is sort of like a success story of backpropagation. So, it was the first one was the first proper one was made by LeCun, and if you go to his website, it's very nice animation. So, I think it was made into a zip code reader, and so he puts zip code like very horribly written digits, and it passes, and you can actually see it saying what the number is. It's pretty good. So, what he did was the way he learned it was backpropagation, but the architecture or the constraints were a little bit different. What he did was alternating convolution and subsampling, which are explained here. So, this alternating convolution and subsampling layer was first introduced by Fukushima in 1980, and he called it neocognitron. So, convolution is essentially, I think it's kind of clear that you have this layer and you have certain weights. So, the weights are fixed. So, each unit has the each unit in a particular layer. Okay, I think plane, yeah. This entire thing is a layer. This single thing is a plane. So, each unit in this plane has the same set of weights, right. And so, you are mapping this entire region, you are taking a weighted average of this entire region and putting it in this pixel. That is your convolution, right. And when you move to the next one, there is this overlap, right. You move to the next one, then it is going to be this square, and that is going to go here. So, there is an overlap, and so you scan the entire picture. So, here I think they have used, so from a 32 by 32 input, they go to a 28 by 28. So, I suppose they have used a 4 layer convolution. Then in the next one, subsampling, what it does is just averages it. So, average in the sense that there is no overlap anymore, you just take the average of this and then put it in this, and in the next one you take the average of this and put it in this. So, this alternating convolution and subsampling is what was proposed by Fukushima and properly implemented by LeCun, and then it goes on, and then here you have this fully connected layer, and then takes you to the output where you have a cost, like you compare it with whatever picture you have, whatever prediction you have, you calculate the cost, and then you do backpropagation, preserving this particular thing, which is all the units shared the same weights. In a plane, all the units shared the same weights, and that did pretty good. This is an example of some convolution CNN. This is one of the middle layers. I don't know if it's the problem with the projector or the fact that I mean this looked actually pretty, I mean it's slightly pixelated, but you can see it was trained on examples of foxes, cars and cats, and you have foxes, you have I don't know what, you have cars and you have cats. So, it was given a cat input, and it's sort of one of the hidden layers, one of the hidden units sort of showed this. Good. So, now how relevant is it to natural brains? So, Hubel and Wiesel did a series of experiments. This is their 68 paper. I think their first one was in 59, where they showed that the visual cortex has cells which have receptive fields, and this receptive fields essentially um, fixate on a particular area in your visual image. In this one, what they have done is they have taken a single neuron, and then so this this empty square box over here is the receptive field of that neuron. The activity of the neuron is shown over here for these examples. So this empty box is the neuron, a neuron's receptive field, and this black bar is what is shown to the cat. Now you see, when it's not aligned, you don't actually see any activity, but when it's aligned, you see an activity. It's semi-aligned, you sort of see somewhat activity, right? So this actually tells you that there is some sort of edge detection happening in the brain. This is another version in the same paper where they put, I think, an electrode through the brain and then on the visual cortex, and so 1 to 10. So they have just considered this, like, you know, which orientation of the black bar fires a neuron. So from 1 to 53, they have put over here the orientation in which the neurons are firing the most. So you can see that at 1, it's like, you know, it fires only when it sees a vertical line, and then gradually as it's going down, it's sort of curving, and then, you know, you can see that as you go along the brain, you have these different regions which correspond to different rotations of the receptive field, right? So this kind of is like an edge detector, and people go on to say that maybe that's what's happening in the brain, which is you first have edge detection, which is in V1, and then you have shapes forming. So I don't know if you remember from the first slide, I'll show you that gradually it sort of looks at even higher order structures, right? So I'll just show you the first slide too. So this is the ventral stream, and they think, like, people think that the in the ventral stream is where these structures get consolidated till it reaches your higher order cognition. All right. But if you add a particular type of noise to pictures, it actually fails pretty horribly, and these are called adversarial attacks. The kind of noise that is there that they've put is essentially you have this is J over here is the cost function, and for getting the cost function for learning, you're essentially doing gradient descent, right? You're calculating derivatives. So that's what's happening over here. This is the derivative with respect to the input of the cost function, and they have just put the signature sign of that as a noise. It actually doesn't have much of a difference, these two pictures, but it actually is very sensitive to that. Also, if you have 1 pixel attacks on these different things, you can see that it said ship beforehand, but with the it didn't say ship, it's a ship, but with the 1 pixel attack it says it's a car, and then horse goes into a frog with a 99.9. A single pixel flip, but there's a caveat, which is it's not randomly chosen. That's why it's called an adversarial attack. It's like an adversary. They actually find this sort of a thing, like the gradient at the cost function, and then realize which are the places where mutations or changes will actually make it crash. Now you can actually sort of get a feeling of why it happens if you look at this guy. You see, there's so much noise in the receptive field, so there, because of its noise, because it's not smooth anymore, you can find a couple of places where if you change, it will fail. Right. So yeah.
Once it fails, is it random what it is saying, or
Is there a pattern? I mean, it's doing wrong prediction, but I don't know if there's a pattern behind it. So the truth is, these guys, or this guy, this guy. I mean, these people, they published it in 2015 in March, saying that it fails horribly. Then in 2015 June, they came out with a paper which some of you might know called Generative Adversarial Networks, which is nothing. You just change the training set. Actually, I don't know. I shouldn't speak about it. But they show it in an archive paper that it fails horribly, and then they come up with the modified version which actually doesn't fail.
So like there's no way to verify that there's an adversarial attack.
As in?
Like, can you verify that a neural network is free of any attacks? Is there a way? Otherwise, how else do you like?
So here what they're doing is they're giving specific kinds of noise or variation which will make it fail. But if you do random changes, like if you just add a random noise, it will probably work out because the noises will cancel. These noises will cancel out with the noises that you are providing. But if you
But they could be like more sensitive cases, right?
The attacks might really affect
for these networks definitely, but I'm not sure for other like GANs or transform like what people have nowadays. Probably not.
Someone asked a very interesting question that if you remove a pixel, right? So in an adversarial attack, if you remove a pixel and say it's a ship, now can you predict that after removing that pixel, the CNN would recognize this as a car?
So you can
Can
again.
you predict what it will mistake it to?
Okay.
The mistake, what the mistake will be? Can you predict that? It will be the output of the one pixel.
I don't know. I think you should take a look at this one. Oops. Apologies.
Just hypothetically, how can we even approach that problem?
I mean, what prediction will it do given that there is a particular mutation?
Yes.
Uh,
And then immune it. If you know what it is going to predict, then you can,
Yeah, I think that's what these GANs are doing. They're not looking at the prediction and then rectifying it. I think what they're doing is they're training it using this these sort of adversarial data.
Because you just drew in the previous slide, you drew a parallel between how the cerebellum is, or the visual cortex, there is a
This one?
gradient-based,
Yes.
gradient-based processing, how it progresses. Now, if there is a problem in any of that path,
Okay, somewhere over here.
yeah,
Okay.
as humans, you will not recognize a ship as a car.
True. Yeah.
Right?
Yeah.
So now, what is it that it is missing?
Correct. Yeah. So
Optical illusions do exist. Some of them might make use of this method of detecting illusions.
But these are not illusions, right? This is not.
It is a computer illusion. The computer is experiencing.
For illusions like this, the CNN will fail miserably because it does not know what it is. What I am trying to figure out is how the brain compensates. If there are adversarial attacks on the brain network, how does it compensate? And
So, I mean, here we can easily say that this is a panda.
yes, for humans, the confidence level would go down. The only thing that will happen is the confidence with which a human would recognize it as a ship. That will go down, but it will
Still
still remain
very
a ship.
significant, yeah.
Yeah. So I'm just trying to.
So I think CNN is not a very good representation
Okay.
of how the visual system is working. So that's why it fails in these slightly modified examples very badly.
But this might be, as he pointed out, optical illusions to the brain. We can
Uh,
objects.
For
Okay,
the CNN itself, nothing of this exists. Everything is an illusion. So it's a pattern recognition itself. So the dog or ship does not mean anything to the CNN. So in that way, if you speak,
You're saying the training data sort of restricts the.
looks for patterns and says, okay, I have been trained and I have been told that
I know that
these
these patterns are the ones which exist. So now if you give me something else which
there
is
is no
not
physical significance.
right.
And
Now, if I remove the same pixel in multiple trials, will the error always be a car?
Oh no, probably not. Yeah. Oh, while after, you remove the pixel and then you train it again.
No. So it's a one pixel attack, right? So we're removing this that one pixel and it recognizes it as car. So in multiple trials, if I remove the same pixel, will the error always be a car?
Oh. Yeah, I think it will be.
Then it's kind of an optical illusion,
Yeah, I think it will be a car if you remove the same pixel multiple times.
Also, can
I can't.
right?
In the final layer,
Or is it like any adversarial point they will always?
no. Here in the final, oh, I haven't drawn it. In the final layer, you have these vectors which say like with this probability this is a frog, with this probability this is a car, airship, whatever, right? I think this 99.7 is that. It's saying with a yeah,
CNN that it is a car.
yeah.
Can we include like generate lots of images based on adversarial attacks on the program and include that in the training?
And
data?
yeah.
Selected,
Probably, yeah.
Label will that
Make it
how
better.
exactly does it modify the neural network to like, when that's included in the training data, what does it do differently?
I don't know. But I think what might be happening is if you put in the adversarial examples like these ones in the training data, then it will smoothen the receptive field. And so then if you have 1 pixel variations or things like that, it will be fine.
So we reduce overfitting by including these in the data.
This is not overfitting.
Because it's overfitting to the data set that is given. So
Ah.
a slightly modified panda, even a very slightly modified panda, it's recognizing as something else. So
I don't think this is same as overfitting. Right. So this is something that I didn't say, but we'll talk about it tomorrow maybe. So deep networks trained with backpropagation get stuck in local minima. So if you have those feed-forward networks which are really big, and you do backpropagation, starting with random weights, they will get stuck in local minimas. Local minima it will not be optimum solution. An example of that is the receptive field that you saw. It was very noisy, and it shouldn't be like that, right? It should be smooth, like certain shapes should come out. Okay, brain does not always require supervision or global error signal. So the supervised way of learning is not how it happens all the time, but it does happen sometimes, like the example we saw in cerebellum. And yeah, backpropagation might be biologically unrealistic because of that weight being sent backwards up to the input. Yeah. If you have any questions, we're happy to take. Yeah. This one?
The right side you show what could be the hidden layers, but
This one?
no, the right side, the schematic.
Yeah.
This is meant to be analog, right?
Yes. So, I mean, this is probably some node in V4 or V2. Yes.
So would you expect hidden layers in human brains?
Uh-huh.
The hidden layers in human brains, do you expect them to have more significant objects, for example?
As you go towards the center?
More meaningful.
Probably, yeah.
So do you think that's why the next slide, does that explain the next slide? Why a single pixel attack does not fool us, but it can fool our machine? Because we have more meaningful categories about what a partner's space is. I don't know, something.
But here also it's the same thing is happening, right? Like, you're essentially lowering the resolution and looking at the picture, right?
But there is no implicit constraint placed on what features it selects.
No, yeah, it arbitrarily picks, yeah.
Picks features, yeah.
So I'm not sure.
just a mashup of some random cars, cats and stuff, right?
Okay.
Doesn't make sense. But is it the case that in human brains you find meaningful activation? Like if you show faces, there is a region which will be activated. Specifically to faces, not this random show.
That's an experiment.
No, so variables in the hidden layer, they don't necessarily correlate to any physical variable, right?
No, in this case it does.
All the variables, no. It cannot be. Some variables, yes. The input and output layer makes sense. But the hidden layer necessarily do not correlate to variables or parameters that we can relate to. We can
Oh, okay,
understand.
okay. For certain examples, some of the layers might not
Yes.
fall
Most
into
layers
particular category.
won't, because you have, so you have, say, you have three variables, say weight and time, say. And now you come up with a third variable that is a combination of weight and time. That does not make sense in itself.
That does not exist over there.
Yeah.
Okay, okay.
But for it exists. It is using it as a variable. But we cannot, because it means nothing to us. It's just we can memorize it and we can put it in writing, but it does not mean anything.
Okay.
So that's the black box part
Mhm.
that comes in.
The thing is, the part of our brain which is involved in explaining or justifying the way we perceive is separate from the part of the brain that actually is involved in the visual cortex.
Recognition.
Our intermediate hidden layers might have equally unexplainable intermediate steps.
But if you want to study them, you want to perceive them in terms that you understand. It has to be understandable.
But if the experiment, it relies on the experimental data. If we find from experimental data that V4 neurons, what they correspond to. So when a particular V4 neuron triggers, it is a random subset of all. So it fires when we see a brown cat as well as when we see a rectangle. That's wholly possible.
As long as it follows the laws of physics, it will.
Okay,
be
one example in this regard. I haven't put the slides, but have you guys heard of the Jennifer Aniston neuron? No. Some. So you show picture. I think it was done to some patient. For everything else, it doesn't fire. It fires only when you show Jennifer Aniston. And so they thought that probably that's like the grandmother cell hypothesis. Like there are particular like one-to-one encoding of objects to neurons, but we don't know if that's the case.
So there is a science paper, 2017 science paper, where they have put electrodes in multiple regions in the cortex, and then showed clips, video clips, and then seen what these neurons that they have tagged fires, and they see what you were saying, very high specificity for specific scenes, and they don't fire for any other thing.
I
So
see.
some neurons will just fire for Mickey Mouse. Whenever Mickey Mouse is on the screen, it will fire. But no matter how close you get to a Mickey Mouse face, it will not fire.
But it's very hard, don't you think, to sort of conclude from that
Yes.
they have like one neuron is
Yes.
like then imagine the amount of stuff that we have.
It
Like,
is something else. So the parameter is something else. But it is being represented in that scene that we just don't understand as of now.
okay, I think Shakti is getting a little anxious.
Okay, so are there any further questions?
Yeah.
You mentioned that the weights have to be same for every day.
Yes.
Piece of the scene. Can you repeat that?
So you have this. It says C1 feature maps 6. So you have 6 planes at 28 by 28. So what it's doing is it has this particular picture and it's making 6 views of that after passing a convolution filter on top of it. That's it. It passes a convolution filter on top of the image. So that's what it is. So that's why each node over here is actually has the same weights on the picture. Yeah, that's what it is.